Welcome everybody to this video on processor architecture. We'll be looking at the fetch, decode, execute cycle, the components of a processor, including control unit, arithmetic logic unit, the registers of program counter, memory address register, memory data register, and the accumulator. We'll also be looking at the cache. To get started, let's have a look at the example we have here. We have instructions all queued up. I want you to think about these questions. In what order do you think these instructions happen? How do you think this might fix the fetch, decode, execute cycle? And are you going to need to decode these instructions yourself? Okay, so have a think about that. I'm going to pause the video, see what you think. Fantastic. Suggestion is that we do these instructions in order. Absolutely. We start with the first instruction and we move our way, I would say, increment to the next instruction as you go down. Okay. What instruction would we fetch first then? We would fetch instruction 1. Now we'll fetch that instruction. To decode means to make sense of it. Does it make sense to you right now? Yeah, you don't need, it makes sense. You don't need to decode that. You can just execute it. So you would just enter the room. Then you would clean your hands. Do you need to make sense of that? No. You would just execute it and then sit at your seat. Now, have a look at this. So we have this separate set of instructions. How are these instructions different to the previous ones? Let's take a moment and have a look at them. The cycle for the processor, as we remember, is to fetch. So we fetch the instruction. We then, previously, we said we needed to decode, but did we actually need to decode on the previous set of instructions? No. Because we read English, we understand it, no problem whatsoever. Do you need to decode these instructions? Okay. We need to decode it because we don't understand what it means. And that is similar to how the processor inside a CPU works. It will have a bunch of ones and zeros, and it needs to figure out whether those ones and zeros are to add, to subtract, to output. It needs to decode. And once you decode it, you can execute it. If I asked one of you, I'm not even going to attempt to try and pronounce one of these words, but if I directed one of you to, or I'm going to do it, Memasuki or Ruanagan, if anybody is, I think it's Indonesian. If you are, I apologize. I'm doing my best, believe it or not. If I asked anybody in this room to do that, what are you going to do?
Open up Google Translate.
Open up Google Translate on it. In fact, by doing Google Translate, what would you be doing? You would be decoding. And then you would be in a position to execute. Is anybody in the room in a position to execute these commands? No. And that is the position that the CPU's in. It needs to decode it to find out what to need to do with it. This was me using Google Translate to translate the original set of instructions. So whether these are in any way accurate, I have no idea. Okay, so this is what an instruction looks like inside a CPU, right? It's all in binary. It's in ones and zeros. So we've got this one here. Again, if I ask anybody in this room to 001, 101, please make that happen. No chance, right? What are you going to need to do? You are going to need to decode it, absolutely. So, yeah, where is the instruction stored? I just talked about that. So where would the instructions be stored? In memory. That might be in cache or in RAM. Cache is small, super fast memory that's on the CPU, but maybe you've only got 8 megabytes of it, so you haven't got a huge amount. So that's like where frequently used instructions are stored. Every time you can fetch from cache, you get a bit of a speed advantage. That's what's good about it. Well, RAM, maybe you've got 8 gigabytes, so it's like 1,000 times bigger, and you can fetch from there. But if you fetch from RAM, it is much slower than from cache. What does this do? Anyone? No chance, right? We need to decode it. And how will it do it? Again, no idea, right? So let's explore it. So in here, I've got my little model of a processor. Let's see if we can identify what some of the things going on here are. So that was our instruction we had originally, and you see it's now stacked in here. What do you think these are?
Memory, order, instructions.
So these are a bunch of instructions. I agree with you completely. What's that? Yeah, they're numbers, absolutely. What do you think they might signify?
Memory addresses.
Yeah, there you go. These are addresses. So do you remember the program counter might say 3, and then you go to memory address 3, and then you'd find the value from here. So these are addresses. So first of all, I'll say that these are all memory. Then have a look. So I'll write that in. Have a look. What do you think this is about? Have a little think. The idea being that each of these are fetched. So we'd fetch one. How do I know which one to fetch? Yeah, so I need the address of where to fetch from, because that's really important, isn't it? Currently, is there anything telling me where I need to which address I should fetch first is? No, we're going to need that. As mentioned, that is the only thing a program counter really does. No, that's not true. One thing, the program counter says, where is the next address I need to fetch the instruction from? So it would be up here. Maybe it says 6. Bingo, then I fetch 6. And then once it's fetched, it increments by 1, i.e. it goes to 7. So that's why the instructions are catch one after each other, a bit like the programming concept of sequence. So anyway, in here, what am I going to write down? The first thing that happens in the cycle is to fetch. Mehmet, what's going to be next in our little processor cycle? So we fetched, let's say we're fetching with this first instruction, 001, 101. What's the next thing that needs to happen to that instruction? Absolutely, we're going to need to decode it, right? We're going to find out what it is that we're supposed to be doing with this. Is it to add? Is it to subtract? Is it to input a value or to output a value? Also, it's probably the value you're trying to add to it. So it might be like, for instance, 001 might be to add. 101 might be to add the value. What's 101 in, if you convert from binary to denary, what's that going to be? Anybody but Jacob, no offense. Yes, Ollie. Beautiful, 5. Hey, and this is the tricky thing. It could be the value 5, or it could be what's held in address 5. Yeah? Anyway, that sounds great to me. So once we've fetched it, we've decoded it, we know what we're supposed to do. Finally, Mirhan, what's the final thing we need to do? Thank you, Guy. Execute is the final thing we need to do. But in this case, execute does not mean to chop off someone's head or any other form of execution. Execute means to carry out, to do it. So the final thing we've got going over here is to execute. Beautiful. So I've got my model here. We've got the first bit. The first bit is to do what? Then I'm trying to make sense of it. To make sense of it, trying to figure out what I need to do. I need to decode. And then finally, what was the final thing I need to do, Mirhan? To execute. Spot on. Thank you, Mirhan. I need to execute to do it. And it's a cycle, so it just keeps doing that in a loop over and over again. How on earth does it do all these things? Well, these are now the components. These are the things that's happening inside my CPU. Also, do you see how I've changed my zeros and ones? I've actually changed them into assembly, which is still the same instructions, but like I've translated it a bit. LDA, guess what that stands for?
Load.
To load something, add, store, out, and then a value here, okay? So I've got my instructions and I've got my data in the same memory location. You wrote a definition down yesterday. Do you know what kind of architecture you have your data and your instructions, like your to-do things, in the same memory? It is, yes, Youssef? Spot on. Thank you so much, Youssef. Von Neumann architecture, I've got my memories holding both the data and my instructions. There are other architectures where they're held separately. So let's go through some of these questions before we identify our components. Give an example of an address that holds an instruction. So I'm going to pause the video, have a look at these ones here. Which one of these do you think actually is an instruction? Thank you, Abdi. So 3, that is just the instruction to out. See these ones here where it says store and a number, also an instruction. So an instruction, it's an instruction with a value. So that's still an instruction. In fact, that's an instruction, that's an instruction. Which one is the only one that's not an instruction? Yeah, 4. Hey, what would I call that? Data. It's just the data. It's just the number. Okay? Give an example of an address that holds... Okay, fine. So an address that holds data is 4. Von Neumann architecture is when both... What did we just say? Yusuf told us is when both... and data are held in the same memory. So for Newman architectures, when data and instructions are held in the same memory. All right, now we need to do some work on trying to figure out what some of these things are. Now, let's see if we can remember what some of the main components of a CPU are. I will very warmly and welcome people just shouting out answers at this point. What do we think? Go on, give me some thoughts. What do you think? Components of a CPU that's going to facilitate, that's going to support the fetch to code execute. Even Jacob, you can shout out. Yes, Elias, go. Huh? Control unit is absolutely one of them. So I'm going to make this one the control unit. Do you remember what the control unit does? It controls stuff. But when you're doing a definition, you never want to use the word in the answer. Yeah. So if it says control unit, it controls the processor, which is not incorrect. But because the word's in the question, you don't want to use the same question again, same term again, right? That's for any kind of exam. That's the deal. Yeah. Well, I'm going to first of all define control unit. So I said control unit manages. That's the phrase I was using. Manages, which is like another word for control, but let's try and avoid it. So what does it do again? Wow, it manages and coordinates the activities of the CPU. That sounds like a fantastic answer, wherever you got that from. Thank you. Connor, arithmetic logic unit. So I'll say this one's here. Say what you see, Emirhan. Arithmetic logic unit. What sort of things do you think happens in the arithmetic logic unit? It's not even a trick question. What is arithmetic? So what sort of things would you think under arithmetic? Like, we're going to do some arithmetic today. Maths, exactly, right? So arithmetic functions like to add, to subtract, that would be in there. Hey, what kind of logical comparisons do you think we could make? By logical comparisons, be like things you do on an if statement. So like, if 8 bigger than 4, yeah, 8 greater than 4, that's a logical comparison. So those are sort of things. Hey, at what stage of the fetch to code execute cycle is this happening at? Jack, what do you reckon? Arithmetic logic unit, at what stage is that going to get involved? Good guess. Decoding is normally the control unit. The executing part is where the arithmetic logic unit. If you think about it, let's quickly run through. We've got LDA4. Let's say I'm fetching that. Load 4. Or even add hashtag 3. Add hashtag 3 gets decoded in the control unit. Oh, I need to add something. I need to add the value 3. Adding the value 3 is going to happen in the arithmetic logic unit. Okay, that's how that works. Hey, we're missing some other things. What else we got here? What else do you think is going to be included on our little map of stuff? What do you think? Go on, Connor. What do you reckon? Who's with Connor? Who's not feeling super confident? Oh, there you go. Thank you, Ollie. Yeah, absolutely, the registers. How many registers do we need to learn about? 4, absolutely. Where do we fetch instructions from? And what types of memory did I say? There were 2 types. I said RAM and cache. Where is cache? Cache is on the processor. Is this the processor I'm doing? Yeah. So cache could be here. Even though cache is tiny and maybe it's only 8 megabytes, cache can sometimes be like a significant proportion of the processor die. It could be like a quarter of the whole processor die is just that cache. Wicked. Let's continue. There we go. Oh, we've talked about this, so we'll go over it again, see what we remember. In the fetch to code execute cycle, explain what the following components do. What does the control unit do, Jack? Which part is the control unit involved with? Thank you, Mohammed. In the fetch to code execute cycle, the control unit helps you decode the instructions. So the control unit helps you decode. The arithmetic logic unit, Emirhan. Thank you, Emirhan. The arithmetic logic unit is responsible for the execute part of the cycle. So the arithmetic logic unit allows you to execute commands, to actually add them up or compare them. And finally, there's cache. Hey, what was cache doing? Cache was storing instructions. And what we're doing, Harris, we're trying to fetch them, right? So the cache will be involved with the fetch part of it. Beautiful, guys. So let's move on to here. those were these definitions. You've got these, haven't you, in your book? Beautiful. So for those who are playing along at home, these are ones that you definitely want to be storing. Maybe not the cache. Yeah, maybe not the cache. So the cache stores, because it can't store everything. Why can't the cache store all the instructions? Because it's tiny. In fact, RAM can't even store everything, but it can store a lot of it. And so the cache stores frequently used instructions. So the ones that you're more likely to fetch more frequently, every time you can fetch it from cache rather than, what was the other place you fetch it from? RAM. You net a little bit of a saving, you get a bit of a speed boost by doing this. Okay? So I'd write down that definition for cache. If you're playing at home, you haven't done this, I get your definition of cache, of control unit and ALU written down as well. So this is the bit where we try to demystify these registers. These look very, very unfamiliar. Program counter, memory address register, memory data register, accumulator. That is not exactly everyday language, right? So let's try and model how they'd actually work. So we've got our memory with all our instructions stacked up. We've got our control unit. We've got all this. We're doing the fetch, decode, execute cycle. All right. What's the first thing that has to happen in our cycle? What's the first stage? The first thing we need to do, Jagger, is to fetch. Which one do I fetch? Mehmet, which instruction do I fetch? We don't know. Something has to tell us where the next instruction to be fetched from memory is. Do you know which one that is? Which register tells you that?
Memory address register.
Good guess. Close. The program counter. The program counter, I've set it to 0. Where's the first place I'm going to fetch my address from? Where's the first address I'm going to fetch from? 0. I'm literally going to fetch from here. What happens next? Here's what happens next. The program counter. So is the program counter currently holding an instruction? What's it holding? It's holding but what does 0 represent? It's an address. And this address gets copied into here. So the 0 gets copied into here. Why don't we just do that directly? Well, because then the program counter has to increase by 1. So instead of 0, it will become 1. What do we need to do now? We've got 0. We want to fetch it. So what's 0? It's this place here. It's saying that we need to copy the contents of here. And what register do you think we'll put those contents into? This one here, the memory data register. So these two, they held addresses. This one is going to hold or in this case, the instruction. Yep. So what am I going to write into here? What am I writing here? LDA. LDA and 4. All right. Now, we fetched it. What happens next in the cycle? What happens after we fetched an instruction? We decode. We have to figure out, what does that mean? What do you reckon that means?
Load into
It says load. Yeah, it says load. LDA is short for load. Yeah? Load 4. Now, in this case, it's not actually loading the value 4. It's loading what's inside, the address 4. So, what is that? 011, 011. Anyone got any quick math going on here?
19. I think.
Well, you thought wrong, so try again. 27.
I don't know where I got that.
It's because you tried to do it quickly.
Yeah.
Jacob, we were all just human.
Single digit math.
And if you were in my shoes, I would say 19 and then go back, delete it, pretend it never happened. Guys, so 27. So we've loaded 27. What register is keeping track of this number? What register did I say keeps track of the number? Which one? We've only got one register left. The accumulator. So in the accumulator, I'm going to write 27. Now, technically, that's wrong. What should I actually write? Because what does the computer store? Ones and zeros. So technically, we just store that. But this is just to make our life a little bit easier. We have fetched we have decoded, we have executed how many instructions? One instruction. What instruction do we fetch next? What register tells us which instruction we need to fetch next? And program counter is pointing to, so we need to put 1, and we copy that into the memory address register. So I copied it in, and now what do I write in the memory address register? What do I write in program counter? 2. What else do I need to do? I need to. First of all, I load, I fetch it. So which instruction am I going to fetch? Yeah, this one here. So where am I going to put add #3? Memory data register. Yeah, what's up? So program counter always increments by 1. What you're asking about, which is I think is quite a deep question, is, well, what happens if sometimes you need to skip to another part? Like if it's an if-else statement, then you might need to skip to another part. And that's called a jump instruction, not on GCSE, don't worry about it. So, but it means that the general way that a processor works is one after another in sequence. So, looking at program counter, it's storing the value 2. Let's remember, is that an address or an instruction? Address. It's an address. It's an address where we're going to be able to find it. We passed 1 down to here, and then we increment, and we made it 2. That's what happens. Now we need to get MAR. Now, is that an address or is that an instruction? Still an address. So we need to then go into memory, and what do we call it? We fetch the contents. So this bit in here, and where do we put the contents? Where do we write that? Into the data register. So the data register is going to actually hold our instruction and data, isn't it? While the other ones are just going to hold addresses. So what do I write in here? What do I write in the memory data register? Add, and then, I don't know why the different colors, #3. Now, last time it just said load 4, and this time it says #3. You don't actually need to know this for GCSE. I'm just throwing it in here for free. You're very welcome. Last time, the 4 indicated address 4, where you're going to get it from. Now it just means literally the value 3. So it's going to add 3. Okay. Yusuf, add 3. Add 3 to what? What do you reckon I need to add 3 to? So we've got the value 3. When you add, how many different numbers do I need to be able to add? What's the minimum number of numbers? 1. You can add 1 number to itself. I need 2, don't I, right? If I'm adding numbers, I need at least 2, minimum 2. So I've got 3. Where do I find the other number I want to add up? What do you think, Jude?
In address 4.
Oh, well, yes, but where do we put that? We put that in the accumulator. Here's how adding works. It takes the value here, it takes the value from the accumulator, and takes them both to where? Which part of this is going to do the adding? In here. Arithmetic logic unit. So it takes the value from the accumulator, takes the 3, it does the add command, and then the result of that, so 27 and 3 is going to give us, where do we put the result? Where do we put the 30? Good guess. Nope. What keeps a running tally? Nope. What keeps a running tally of the value? Accumulator. So the accumulator, we took the 27 into the ALU, we took the 3 into the ALU, we added them to make 30, and the results of that are put into the accumulator. So what do I put in the accumulator? 30. You see how that works? What part of the instruction have we just done? We've executed. So we've executed, so now we need to fetch. What do I fetch? So what do I need to, which address do I need to fetch? 2. So what do? I move the value from the program counter. What do I do with it? I put it into the, so I make a copy and I put it down here, bless you. So I make that 2. Anything else I need to do? Increment program counter by how much? 1. So that becomes 3. What do I do with 2? I look in the contents. Yes? For that instruction, where do I put that instruction? I put it in the data register. So in here, I'm going to write down, what do I write down in the MDR? STO STO. And then what? 5. Right. What stage of the cycle am I currently on? I've just fetched. So what do I need to do next? Decode. What on earth do you think STO means? Hey, Mehmet, you need to stow. Stow it. What do you think? What do you think STO could stand for? What do you reckon? Store. Good guess. Store. Do I store the number 5?
In the address.
Yeah. So store means store at position 5. So it's currently blank. So I can store something in here. What should I store in here? What should I store in here? The value in the accumulator. So I take this 30 and I put it into position 5. You see how that works? I'm going to write the word 30. Why am I wrong to do that? It should be ones and zeros. Exactly right. Am I finished? What's next? I've just executed, so what's next? Absolutely. Fetch. What should I fetch? 3. So I put 3. What do I do with it? I copy it into the memory address register. Put 3 in here. Anything else I need to do? So program counter becomes... anything else I need to do?
Move the program in the address of 3 to the data register.
So I've got this 3. I've got this command. Where do I put this command? I put it in the...
Data register.
Right. So this is my fetch bit almost finished. Now before, it was always like a command and then a value, right? Command, value, command, value, command, value. Now it's just the command out. We need to decode that. What do you reckon out might be? Output. What am I going to output?
The value in the accumulator.
And it would just output 30. How much of a pain in the backside was that? It was a real hassle, was it not? And in the end, what did we actually achieve?
We took the number 27, added 3.
26? Oh, 27, yeah. 27, added 3 to it, stored it, and then added it. What a hassle. How long did it take us? A long time. But the whole point is, this cycle, how fast is this cycle happening? No, in a computer, how fast is it happening? Yeah. When we said 2 gigahertz, what did that mean again? 2 billion times in a second. So you can see that although for us it's a right pain to see it stage by stage, the real power of a processor is how rapidly, even though for us it's going to take forever, how long is it going to take the CPU to do this? It's nanoseconds. Like you can't even perceive, it's so quick you won't even perceive the time it's going to take. That's how quick it's happening. All right, people. And like a recap again, program counter. Do you know what, actually I don't need to do a recap. On the next slide, there's going to be some questions for you to link up. There'll be a good opportunity for you to do a task. See this? Those are the 4 registers. On the right-hand side are the 4 descriptions. I want to pause the video now. I want you to see if you can match up which is which. So, looking through these questions here, we've got the accumulator. We've got a bunch of different results. The one we're going to go for is it used for temporarily storing arithmetic and logical results. Remember, when we added the numbers together, we added 27 to 3. Where do we put the result? We put it in the accumulator. Beautiful. There we go. Accumulator it is. Right. Then we've got a bunch of other ones. Now, we're anticipating that program counter and memory address register, will they hold instructions or will they hold addresses? MAR and program counter will both hold addresses. And the memory data register, that can hold the actual instruction. So, which one of these are these descriptors saying it just holds an instruction? 3. So 3 is going to be what? So that's, which one of these is holding, the memory data register, that holds an instruction. Or potentially data, actually. Instruction or data. While these two, program counter and memory address register, what do they hold? They hold an Address. Beautiful. So memory data register goes across from here whoop, to here. Sound effects are for free. You're welcome. And then we've got a bit of a conundrum then, haven't we? We've got these two. We've got one of them says it points to the next instruction that needs to be executed. It's located in the control unit. And we got the other ones used for holding the address of the current instruction to be executed and the address of data to be used in the instruction. Do you know which one's which? First one's the program counter. And then by process of elimination, memory address register is the other one, because this is points to the next instruction that needs to be executed is the definition of a program counter. I'll run out colors. Oh, there we go. Doop, doop. Sound effects are for free. Beautiful, guys. Let's have a look at another question then. In fact, what we got here. This is actually an exam question. Look at this. 4 marks. You only have to do is tick the right boxes. Piece of cake. Am I right? I know. But these are the type of questions you might get for this. So let's have an opportunity to look at it. It says the table has 5 components of a computer and 4 statements. So these are memory address register, memory data register, the cache, the program counter, and RAM. So these are 5 components. Tick 1 or more boxes. So is that 1 box for each? No, it might be 1, might be 2, might be all 5. You need to evaluate all of these. It stores a single address. So you need to figure out which one of these might store a single address, which one might stores the frequently used instructions, which one's a register, which one stores all the data currently running. I'm going to leave that there. I want you to pause the video. I want you guys to have a look at that and think about which one's which. And if you've got a book with you, maybe you make the table. This might be a little activity. Write the questions down, make the table, and see if you can figure out which one's which. So the first part, the first statement we need to evaluate is it stores a single address. So which one of these stores a single address? Jamie, what do you reckon? So you put PC. Well, just go for your first instinct. You put PC. Anything else? Now, why did you change your mind? But does it still hold a single address? Guess what? You're right the first time. So it is program counter and memory address register. They hold a single address. Does MDR hold a single address? No, it holds instruction or data. Cache, frequently used instructions. I'm going to give them the game away here, aren't I, already? And RAM, well, that's holding lots of stuff. It stores frequently used instructions. Who's not had an opportunity for a little while? Ooh, Ben, frequently used instructions. What do you think? Cache. Anybody supporting Ben? 1 person, 2 people, 3 people, 4, 5, 6, 7. Oh, there you go. See, 8. Yeah, you're right. Cache is frequently used instructions. This is a bit where I kind of disagree a little bit with the exam board in the sense that cache actually in a modern architecture often holds data as well as it. But whatever. This is not computer science according to me. It's computer science according to OCR. Hello.
Could you not also say RAM? Because among other instructions, it does also happen to store.
I suppose, but it specifically stores frequently used instructions. Why does it? The advantage of cache, remember, it was a lot smaller. But what was the advantage of cache? It was a lot faster. And so, but because it's small, you want to put the frequently used instructions in there. It is a register. So we need to identify which one of these are a register. Murat, what do you reckon? Registers. MAR, MDR, and PC. Anybody agree with Murat? You have a similar, even faster support base going on there, Murat. Yeah, I completely agree with you. Cache is not a register. It's a component of a CPU. Is RAM a component of a CPU? Is the RAM inside the CPU? No. RAM is part of the whole system. And then finally, it stores all currently running data and instructions. So all currently running data and instructions. Yusuf, What do you reckon? All currently running data instructions. That's all, like, it's not the stuff that you got stored for later. It's all the stuff that you're currently running right now. Where's that stored? Youssef is suggesting RAM. Does anybody agree with Youssef? Your support is thinner on the ground, but still quite widespread. Youssef is absolutely right. It's all currently running data and instructions. The stuff that's not currently running would be on secondary storage, wouldn't it? Yeah, on your hard drive. So when I talked about loading up your PlayStation, your Xbox, whatever you happen to game on, right? When you load the game, it loads it into RAM, ready to run. Okay, identify the name of one register not given in part A. What's the one thing we haven't got? Accumulator. What does the accumulator do? I'm not going to write it down. It was on the last slide. It keeps track of the running, temporarily holds results from the arithmetic logic unit. Yeah, it gives the results of it. Fantastic.